All right. So picking up where we left off, last week I skipped over section 2.3. I'm going to pick up on 2.3 today, and then we're going to get into 2.6 a little bit. So what 2.3 is really all about, it's just going to be this idea of interpreting the derivative as a rate of change. That's really all it's measuring. And we can see that just by looking at the fact that, well, the difference quotient, that's what we're starting off with, right? And what the difference quotient measures is the average rate of change between x is equal to a, x is equal to b, right? So if we have some function, actually from the next slide. So if we have some function, x equal to a, x equal to b, what the difference quotient, what would be this dotted line here, the hypotenuse of that right triangle, what it would be measuring is going to be what that secant line is going to have as a slope. And what the difference quotient is going to be measuring is the average rate of change of our function between x is equal to a, x is equal to b. So the slope of this secant line is going to be equal to the difference quotient, and that's going to be the average rate of change. To see some of this, let's consider this example here. Finding an average velocity. We're given that this thing, whatever we're talking about, in this case, it's going to be an object being dropped from 100 feet, right? That it has a height function associated with it as it falls of -16 times t squared plus 100. And if we want to know what the average velocity of this thing's going to be for any chunk of time, well, then what we're going to want to do is find out what delta y over delta x is, right? Or in this case, delta h over delta t. Well, that's just going to be the difference quotient. And what we're going to do is we're going to say h of t plus delta t minus h of t divided by delta t. We're going to work this all out, right? When we do, we're going to get that this comes out to be -16 t plus delta t, that quantity squared, plus 100 minus -16 t squared plus 100, all divided by delta t. But we can draw our square brackets, can't we? The first term, or the first set of terms. And here we can distribute this negative sign all the way through and then drop the second set of square brackets, right? So doing that, I get this thing. Well, right away we can see the hundreds are going to cancel, right? And then we can see that we need to expand this out, yeah? So we're going to get -16 times t squared plus, let me make this minus, 32 t times delta t minus 16 delta t squared plus 16 t squared all over delta t. Well, this is going to cancel with this, right? From here, we're going to be able to cancel out each of these delta t's, right? So lower this by a term, by 1 power, and then cancel this delta t out. Agreed? So what we're going to be left with is negative 32t minus 16 delta t. Okay. So I'm going to go ahead and erase all this work. So now we have an equation for the average velocity for any given time interval. Agreed? So let's look at this part A here. Part A wants us to find the average velocity from time equal to 1 to time equal to 2. And we know B is equal to A plus delta T. Agreed? So looking at the time interval, plugging everything in, this is going to give us that delta T is equal to 1. Right? So now the question is going to be, what do we want to use to represent as t up here? This t is going to be our initial t, t naught. Make sense? Because it's where we're starting from to where we're going. So let's just call this t naught for t initial. So throwing now all of this back in, we're going to find that delta H over delta T is equal to negative 32 times, well, our initial T here is going to be 1, minus 16 times our delta T here is going to be 1 again, or it's going to come out to be negative 48 feet per second. Over the time interval one to 2. Make sense what I mean?
What's the 1 to 2?
That's our time interval.
Oh, okay.
So looking back at everything, we know our time interval, A to B. That's going to be equal to 1, 2. We know how A and B are related together, right? B is equal to A plus delta T, so from that we were able to find out what delta T is. And from that, we were able to find out what the average velocity is. Negative 48 feet per second squared, or per second. So looking at everything, negative 48 feet per second. Now, having said that, we didn't have to go about it this way. We could have calculated what h is at time 1. We could have calculated what h is at time 2 and just gone about it that way. That's what they did here. And then divided it by whatever that change in time is. Make sense what I mean? The way we went about it is a more general formula that lets you solve all of these more quickly. So there's two different routes we can go here. If we have a bunch of these different questions related to the same function, we can go about the way I just did it on the board, because it'll save us time in the long run. But if we only have one or two of these, maybe we do go with this method of just calculating what h at 1 is, h at 2 is, delta t is, and then applying the difference quotient. What do you mean? So having said that, if the difference quotient measures the average change, the average rate of change, well, when we take and we move B really close to A, right? We apply that limit to it. Then what the derivative must be measuring is going to be the instantaneous rate of change. And by that, what I mean is, if I'm walking along, at any given moment in time, I'm going to have some velocity, right? But from the moment I start walking, you can say right now to right now, what is my average velocity? But we know, though, like I said, in this moment right now, I've got some velocity, right? That's what the derivative measures, is in that moment. Everybody cool with that? Yeah. No, not so much? Oh, I thought you said no.
Oh.
So again, this idea of the derivative is saying, at a moment, what is your velocity? Or at a moment, what is your rate of change? All right, so we found out what our average velocity was in that first problem, right? We said that the average velocity was negative 48 feet per second for 1 to 2, right? But what's the instantaneous velocity? Well, the instantaneous velocity, we're just going to apply the derivative to our function. So that's going to give us negative 32 times t. Agreed? And then we're just going to plug in 1. Just negative 32, right? So your speedometer in your car, what it's measuring is a derivative. Every time you look down at it, it's measuring what your velocity is in that moment, which by definition is the derivative. Having said that, looking at this really quick, we had our position function, we found our velocity function, we plugged in 1, we got negative 32 feet per second. Everybody cool with this idea? Okay. Well, looking at this first question in this problem, well, stepping back, in this particular problem, what we've got is somebody jumping off a 32-foot high diving board with an initial velocity of 16 feet per second. Why they're doing that, I don't know, they're extra. So they jump off, and the question is, when are they going to hit water? Well, presumably when this position function is equal to 0, right? Well, that seems like a reasonable assumption. So the solution to this first question is going to be found in one of two different ways. We can set our function equal to 0 and apply the quadratic formula, which I know everybody loves to do that. Or we can go about it by factoring things out. In this case, what we can factor out, h is equal to negative 16 t squared plus 16 plus, my mistake, 16t plus 32. We can first start by factoring out that negative 16. We're going to get t squared minus t minus 2. So now we can factor this out. We're going to get negative 16 times t plus 1 times t minus 2. Everybody agree? So this thing has two different zeros. One is at negative 1, the other one is at 2. Now the question is going to be, which one of these makes physical sense? Well, time doesn't move backwards, so presumably the positive value, right? So we just solved the first part. Do Buddy McGee is going to hit the water when time is equal to 2. Seems like an awfully long time to fall. Now, the second question is, what was their velocity when they hit the water?
Is that the derivative?
It is the derivative. Because it's the instantaneous change of their position, right? That's what velocity measures. Agreed? So h prime is going to be equal to negative 32t plus 16. That's it. Right? Well, we know that time is going to be equal to 2. So now we're just going to plug in 2 into our velocity equation and find out the rest. So negative 64 plus 16 should come out to be 48. Negative 48, I mean. 38. Why can't I do simple math today?
Negative
Yes,
60.
that's right. 48. Right? I can't do simple math today, apparently. So 32 times 2 plus 16 is going to come out to be negative 64 plus 16. So yeah, negative 48. Is everybody cool with this? So just to reiterate, what we've got is some asshole who decided to jump off a board into water. I don't get it. Like, why would you do this? I had to do it in basic training and I hated it. Anyhow, looking at what they've done, they went through and they used that factor method, right? To solve for when our function is equal to 0, when they hit the water. That way they were able to get what t is equal to. And then they calculated what the velocity function is using the derivative and plugged in 2 to find out how fast they're moving when they hit the water. And I forgot my units again. Units are important. So says the physicist anyhow. So question. If velocity is equal to the derivative of the position function, what do you think acceleration is going to be equal to? Acceleration then is going to be equal to the derivative of your velocity function. But more on this in a little while. For now, I just wanted you all to see that and to think about it for a few seconds. Moving on though, because this is business calc, we want to connect this to business. We have these things in business that we are all familiar with, the idea of profit, revenue, and cost. Profit is going to be whatever's left over from your revenue after you take into account the expenses that you've incurred. But how do those things change? And what do we call them when they do change? Well, the instantaneous change of profit is going to be called the marginal profit. Of revenue, it's going to be marginal revenue, and of cost, it's going to be marginal cost. So the instantaneous change of any of these terms is just going to be the marginal followed by that associated term, right? So what does it mean in the context of business? All right. What this problem is going to ask us to do is to find first the derivative of our function at 50. And then it's going to say, all right, we know what the rate of change is at 50. Let's compare it to what the average change is, the actual rate of change from 50 units to 51 units. So finding out what marginal is, P prime is going to be equal to 3 times 0.002 x squared plus 10. Agreed? Yeah. So this is going to come out to be 0.006 x squared plus 10. I'm sorry, say what?
It's 3 zeros.
Oh, it is 3. See, I thought I was missing a 0. 0.6, 0.2. So now we're just going to plug in 50. Oh, it's going to come out to be some crazy number that I'm not even going to pretend to calculate right now. It sounded like somebody was getting out a calculator. Are you typing it in for me? Awesome. While you're doing that, try to find out what the actual change is from 50 to 51. Well, that's going to be P at 51 minus the profit at 50. Which is going to come out to be 0.0002 times 51 cubed minus 0.0002 at 50 cubed, right? Because the 10s are going to cancel, the 10 t's. My mistake. There's a X on that. Zero, zero, 0.0002 times 51 cubed plus 10 times 51 minus 0.0002. God, this problem is tedious. Cubed plus 10 times 50. Right? Now, I'm not going to pretend to actually do these calculations in my head. I am instead going to jump to the next slide and say, voila, the derivative, the marginal profit, is going to be $11.50. And the actual change is going to be $11.53. Now, why isn't the marginal profit equal to the actual change? What do y'all think? Any thoughts? The reason why is because what the derivative measures is the rate of change at a point, right? But that rate of change can change moving your point. So if you change your x value, your rate of change is going to change. But really close to your x value, it's going to be approximately this. Does that make sense what I mean? So another way of thinking about it let's say we've got the function f of x is equal to x squared, let's keep it simple. The derivative of that function is going to be equal to 2x. Now the derivative evaluated at, let's say, the point 5, that's just going to come out to be 10, isn't it? Right? But the change from 5 to 6, that's going to be 6 squared minus 5 squared, or 11. Agreed? Now the reason for this, like I just said a second ago, let me actually erase all of this. The reason for this is because we look at what we've actually measured. The derivative at 5 is going to give us the slope of that tangent line. Yeah? But that total change, it's going to give us the slope of the secant line, which isn't the same as the tangent line. Does that make sense what I mean? Now notice in the example on the board, or I mean in the slides, and on the board, works out that what we calculated with the difference is the slope of the secant line because the change in x is equal to 1, right? Makes sense what I mean? So by dividing by the change in x, it's no different than saying what's the difference from f of b to f of a, or vice versa. So some hand waving aside, the point of this is to say that the difference quotient gives you the slope of the secant line from A to B. The derivative gives you the slope of the tangent line at a point, which are going to be different slopes. Something else worth noting. If we were to zoom in on part of this, what we would see is something that looks relatively straight, right? If we were to zoom in really close onto our graph. So if we choose some A value, if we choose a B value close enough, the slope of that secant line is going to be pretty close to the slope of our tangent line. Make sense? So for really close numbers to whatever our A is, the difference quotient and the derivative will be about the same, but not identical. They'll be off by decimals. But the further out you get, the bigger that discrepancy gets. Having said that, I'm going to jump to 2.6. So the question here is, can a derivative have, or can you apply the derivative to a derivative? Well, if we think about what it requires to apply the derivative of something, that's continuous, where we're trying to differentiate it, then sure, why not, right? Derivatives give out functions. So long as our function that the derivative evaluates to is continuous, where we're trying to differentiate out a second time, why can't we? For that matter, why can't we do it a third, a fourth, a fifth, a sixth, a seventh time? Why can't we do it infinitely many times? So as an example of this, traditionally, when we talk about projectile motions, right, the act of measuring the path that just took. When we talk about this, we talk about it in two parts. We talk about the x direction and the y direction. This is the equation we generally apply when talking about what happens in the y direction. This function here is the general equation for measuring the height of an object falling under the effects of gravity. Now, knowing that, the derivative of this with respect to time, that's going to be the velocity function, right? We just talked about that a few minutes ago. dh dt is going to be equal to the velocity function, or at plus v. But hey, notice this velocity function, I can differentiate it again, couldn't I? So why don't I do it? And that gives you the acceleration. Now, acceleration, this function is a constant function. So I can differentiate it again. Differentiating it again, dA dt it come out to be 0. My bad, it's J, not S. Now you might want to know, just out of curiosity, what happens after acceleration? It measures what's called jerk. And then the derivatives after that would be snap, crackle, and pop. I'm not kidding, that is literally what the physicist named it. And these are just different measurements for how fast a thing is changing. And one way we can interpret acceleration is how fast the velocity is changing. The jerk would be how fast the acceleration is changing. Snap would be how fast jerk is changing, so forth, so on. But I don't like this notation necessarily. Because this thing, well, this thing's dH dt. We've already written that. I'm going to write it again. This thing, acceleration, it's d dt of dH dt. We have to write it slightly different. And finally, what we've got at the bottom is d dt of d dt of d dt of h of t. So we're applying a bunch of different derivatives. But these suck to write. So let's come up with some abbreviated notation. Actually, I think it's on my next slide. Sweet, it is. All right, so for some abbreviated notation, because like I said, that sucked to write out. The first derivative can be written as y primed, f primed of x, dy dx, d dx of the function x, capital D subscript x of y, bunch of different ways. The thing I want you to notice is that in the prime notation, after the third derivative, we use parentheses with the number of derivatives in that parentheses. So if I were to write that's a 10th derivative of whatever that function is. Similarly, on the d's, we might also write d10 dx to the 10th power f of x. So forth, so on. As long as our function is differentiable, we can do this. Make sense? So as some examples, let's say we've got this function, polynomial of the 4th degree. We want to take the first derivative of it. Check out the notation. Moving all the way through, the notation changes, right? So if we wanted, in this case, to find the third derivative at 2 of this function, we would apply the derivative once, we'd apply it a second time, and we would apply it a third time. Once we got to this point, we'd say, all right, cool, let's just go ahead and plug in 2 now. Everybody cool with this idea? So the 4th derivative, as an example, of 1 over x, we had that -1 power, bring down the -1. So y prime is going to be -1 times x to the -2nd power. Do that again, but now you have -2, and your power is -3 now. So you're going to have 2 over x cubed, then 6 over negative x to the fourth, so forth and so on. So the rules don't change here. We're doing the same derivative. We're just doing it over and over and over again, right? So back to that point of acceleration, velocity, and position. The velocity function is your derivative of position. Acceleration function is the second derivative of position. So obviously this stuff is going to be useful, particularly to like physicists, chemists. There are some parts of econometrics that uses the second and third derivative. Where else does it show up? Biology, a lot actually in biology, more recently than in the past. Where else does it show up? Your car, driving, so forth and so on. So I'm going to go ahead and skip all of these because we've talked about them in excess now. All right, section 2.7. This, you're gonna wanna spend some time on. I'm not gonna like candy coat it or anything. It's weird, it takes some time to figure out. This was the hardest part, I thought, of calculus when I took it. And it's just because it's weird. Like getting used to it takes some time. And that's really all it is. So having said that, there is what's called an explicit function and an implicit function. An explicit function says y is related to x in an explicit way. It says clearly this is how y relates to x. Explicit functions can be written in the form y is equal to something without y in it at all. Make sense? I argue that this thing is an explicit function. The way how, or the reason why, I can't talk. The way we can see that it's explicit is because we can divide out that x and get y is equal to 1 over x, right? When we do that, we get our explicit function and then we can differentiate it. Having said that, there's what's called the implicit function. The implicit function is something you can't separate out like that. So no matter how hard you might like to try, there's no way to get it into a nice y is equal to something, right? So one example of this, solve for y here. Well, when you solve for y, you get y is equal to plus the square root of 4 minus x squared, or minus the square root of 4 minus x squared. It's not a simple functional rate, right? Notice what else? This thing's the circle. With radius 2. That's not a function at all. It's just an equation, right? So moreover, we have implicit and explicit equations as well, not just functions. Now, having said that, we're given just that. We want to find the derivative of that. We want to find all the tangent lines. How would we do that? We would use what's called implicit differentiation, which basically is applying the chain rule. What we realize, or what we need to note here, or to keep in mind, is that this y, it's an equation of x. So, by the chain rule, this derivative, first thing we have to do is differentiate as if it's u, right? So we're going to get 2y. Then we're going to have to differentiate the y. We're going to get dy dx. This is what I mean about it being strange. Is everybody with me so far? Sort of. So, having said that, we just kind of did a problem like B. Let's check out D. How do we go about solving D here? No, what I just did wasn't the derivative of the entire equation, right? Like it wasn't the derivative of x squared plus y squared equal to 4. It was just of that one term. Just wanted to point that out. So here we want to apply the derivative to x times y squared. Well, this is going to be equal to y squared times the derivative applied to x, agreed, by product rule, yeah, plus x times the derivative applied to y squared. So what we're going to get is y squared times 1 plus x, we just saw this, was 2y dy dx, which we can reduce further to y squared plus x 2y dy dx, and if we wanted, we could factor out a y. What are we doing here? We're thinking of everything that's happening to y as a function or as an equation. And then we're differentiating y. So you can think of u as being equal to y squared. So du dx, well, that's going to be equal to 2y, right, times dy dx. The chain rule. Does this make sense to everybody? So really quickly looking at the solution to that last problem, 2xy dy dx plus y squared. They just rearranged the order. I think. No, I don't. Okay. So differentiating implicit functions. Like I said, the easiest way I know to think of this is to ask myself what du dx is. Du dx is equal to du dy dx. So du dy, well, that's the derivative that I had just written down. That's that thing, right? Which is going to be equal to 2y. Then dy dx, well, we don't know what that is because y is implicitly described as an equation of x. So we just have to leave it as dy dx. What time is it? 16 more minutes. All right. Let's look at this last example here. Now notice in this example, we could solve for an equation of y, but it would be a piecewise equation, right? We'd end up with that plus minus thing and blah, 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 blah. So that means we have to find a bunch of derivatives as opposed to just finding one. If we want to find dx of x squared plus 4y squared equal to dx of 4, well, this derivative is of a constant, so it becomes 0 right away. Now the second part, we can distribute the derivative through, right? By rules of derivatives. So dx of x squared plus 4 times dx of y squared. Well, we've seen this now like 3 times. We know what this is. This is 2x plus 4 2y dy dx is equal to 0. We're getting close. Now we want to find out what the derivative of y with respect to x is at those points. Agreed? So to do that, first thing we're going to want to do is to try to solve for dy dx. So we're going to subtract 2x from both sides and then divide both sides by 4 times 2y. Everybody cool with that? So we've got 4. Just go ahead and write 8y dy dx is equal to negative 2x so dy dx is going to be equal to negative 2x over 8y or negative x over 4y. Everybody agree with me?
What is the negative 2x?
So what?
Huh?
I didn't hear you, I'm sorry.
What is the negative 2x? I don't know where that's coming from.
That is coming from the derivative of x squared.
Okay.
Make sense? So the sum of difference rule is what we applied right away, right? That's how we were able to break up this derivative into two others. And then here, the constant multiple rule is how we were able to pull out that 4. So then we said, all right, let's evaluate this derivative. That gives us the 2x. Let's evaluate this derivative. That gives us 4 times 2y dy dx. And the derivative of a constant 4, well, that's just 0. So now we have an equation for the derivative of y with respect to x. This is going to give us, again, the slope of our tangent line. So from here, all we have to do is plug in the square root of 2 into negative x, and negative 1 over the square root of 2 into y. And that gives us the derivative at that point. Is everybody cool with this? So notice really quickly, this equation is the equation of an ellipse. If we were to solve for y explicitly, we would get these two different equations, one for the top part, one for the bottom part. The point we're talking about is this point right here. This is the point we want the slope of. So doing everything, applying that sum and difference rule, we can go ahead and get to this point here where we break everything up. Like what I've done here, right? Then solving for dy dx, we get negative 2x over 8y or just negative x over 4y. I'm plugging in square root of 2 for x and negative 1 over the square root of 2 for y. We get 1/2. So the slope of the tangent line at this point is going to be 1/2. Which makes sense, right? Like, look at this line. It's got a positive slope. It's not quite equal to 1, but it's not quite 0 either. It's somewhere in between. It's halfway in between. Yeah? Is everybody cool with this idea? This is what I mean about it being strange, because it does take some time to get used to. All right. This is a beast. That's what it looks like, right? But notice here, you're going to get a dy dx. Here, you're going to get a dy dx. Here, you're going to get a dy dx. So you're going to be able to factor out a dy dx wherever you go, right? Here, you're going to get a 0 in your derivative. So you're going to be able to start solving things this way, right? And what we're looking for, it's going to be the derivative for this equation. I feel sorry for the computer that had to graph that. So after applying the sum and difference rule and applying implicit differentiation, we're gonna get 3y squared dy dx plus 2y dy dx minus 5 dy dx minus 2x is equal to 0, right? 0. It's the derivative of a constant. We're gonna be able to move this negative 2x to both sides. And then we're gonna be able to factor out a dy dx. That's what we do here, right? These two next lines, or those steps combined. So factoring out the dy dx. Now we can divide both sides by this polynomial. And we get that the derivative dy dx is equal to 2x over that polynomial. What do y'all think of this? It's going to take some time, right? Well, having said that, we've got 5 minutes left and a bunch more of these. So I'm going to let y'all go. If you have any questions, by all means, please feel free to ask. I'm going to stick around for a few more minutes.